Hello, Matt.
Hello.
How are you guys? I got your submission for the extra credit today, but it turns out the extra credit the deadline I made was on Monday, so many others couldn't submit apparently. So I realized from a few minutes back.
I think I seen that, a few days ago.
Yeah, I think you managed to submit it because it was before the due date. You submitted before Monday, all right?
Yeah.
Yeah. So it turned out that it is on Monday, but I think I intended to make it on Wednesday. Curtis, I got your email about the extra credit. I'll mention it in a few minutes.
All right, sounds good.
Hello. So we have 4 of us, I think, 2 are absent. Correct. A bit confused because I am also there. Yeah. I think it's Riley and Travis. I think. Okay. There was a small confusion regarding extra credit. I intended to have the extra credit this was 0904, I suppose. That was the last date.
Yeah, it closed on Monday.
Yeah, it closed on Monday, but yes, did you also try?
I was trying
Yeah.
to.
That was not my intention. It was my mistake. I just went by the next class. I didn't realize it was a holiday. So I'll give credit to everyone. Credit to everyone. Okay. So if you Gordon, you might be the one who might lose, but I think others try to do it. So if you don't get it updated, just let me know. Just track it. I intend to do that maybe by end of today. So
I'm the one that doesn't get credit, or
no, you will show. You should get credit. That will be not fair if you don't get it. But I was saying, how is it? Relatively speaking, how do you say this? If everyone had got a 0 and you had got a 1, so that advantage is not there. But I think extra credit anyways. So many of them. Okay, so in that sense, I was saying you're the only one submitted. But that is all. I'll never know because others might have tried to submit and that might not have worked out. Because usually it is the next. Okay, it's reasonable to do. So make sure you get credit for that. I'll do that at the end of today. And there's the homework 5, which was due today, but that's over, right? So we don't have to mention that. How did the homework 5 go?
I wasn't 100% sure myself.
yeah.
Yeah. I turned it in before class, but I would have rather kind of taken a couple days. I'd like to see the feedback on it, but I don't think I was fully comfortable with it when I submitted it.
Oh, that's not good to know because I was planning to put the exam based on that. Okay. Any comments from Matt and Curtis?
No.
No, not at the moment.
Yeah, the question was, how was the homework, and if the exam is a a good percentage of it is based on that. By good percentage, I mean 40% or something is based on that. Would you be comfortable? Did you have any issues with how the homework went? Would you like me to go over the homework or something like that? But I intended to do something on cylinder also today, but we can stick to spherical symmetry. That's also possible. So the question was, how comfortable are you in homework if 40% of the exam might be based on that?
I think I was
comfortable with it.
Curtis, you were comfortable. Matt?
Yeah, same.
Same, okay. Yeah, so let me see while I write this, let me think about it. So midterm one, surely we decided that this is going to be a take-home examination so that everyone doesn't have to come. So take-home exam. And it will be take-home also in the sense that it won't be a one-period exam. It's not a timed exam. That will be sufficient time. So it will open, let's say, I'm giving the time of during class, but it might even open before. So surely by 2 p.m. on Friday, but even before. Once I have the exam ready, I will just open it. It will be available at the same place as usual on the website, and it is due on next class. So before the next class, let's say. Before next class. Is that clear enough? What I mean there? So if it is that long, would you feel comfortable with the homework? If it is 40% based, would you be able to go and search and be able to learn things? And I will do some examples today also, slightly more. I was planning to do most of it cylinder based, but maybe I will go back and do one problem on the sphere where there was A less than B problem. I think it was the second or third problem, I suppose. I can try to do that and then come to the cylinder. So hopefully it will work. Okay. So
if we turn in the homework, how quickly will we get results back?
Oh, yes. So pretty quickly, I will give priority to that. So what you could do is that you could send me an email saying that I've done the homework, please grade it, just grade it, right? So I will then immediately do that. It's just as a reminder, that email is just for a reminder. I intend to do that today.
Okay.
Oh, because it is due on Friday, right? Oh, that's the problem. Yeah, so once you finish the homework, just let me know. After tomorrow afternoon, surely. Okay. Because then I will be doing only this course until tomorrow afternoon. I have things going on. But even today evening, if you finish it, I may not be able to grade it tomorrow morning. That's all. Does that help?
Hmm.
So homework 3, right? No, homework 5. Let's do Friday. But you're in class, so this is September 11. I think it's clear. Okay. September. Okay. Is there any confusion? Or when you're in class, September 11, you opt before next. Okay, so let's do an example in the homework. Did I do that homework? No. I think the problem was the example of the example of Gauss's law. This is from the homework. You're given a charge density. Remember, Gauss's law deals with. That's right on the question. So given rho of R is equal to
It was.
yeah,
If you want
yeah, sure, it is exactly the
to
same.
K over R squared.
K over R square. K over R square for R less than A, right? And after that,
Oh no, I think that was for R in between A and B, A less than R.
and is it 0 in the? Oh. So it's 0 for R less than A, K over R square for R less than A and greater than B, and it is 0 again for R less than RB. And find the electric field everywhere. By everywhere, it means that for less than A, since it is spherically symmetric, you only have to worry about the radius. If you're inside A, between this, so what is the charge distribution? So how does it look like? So we have, so this is a sphere. That circle represents a sphere. It comes out of the board. Also, that's radius A, and that's radius B. So that's your A, and that's your B. Right. There is charge down here. Right. Otherwise, it is 0. And it is not uniform in this region. Notice when R is less, charge is more, so there is more charges here. If you want. That means concentration wise, there is a gradient of charge there, so there is more charge closer to A and less charge across closer to B. If I were to tell that this is a perfect conductor, is that possible? Christian North said, he says that's not possible because in a perfect conductor, all the charge try to stay as far as possible. So they will all tend to be on the outer extreme. So it cannot be a conductor. We know that this is a dielectric. So that's just an added point. So that's your configuration, and we want to find electric field everywhere. So let's begin from inside. So we begin with our Gauss's law. Gauss's law tells that dA for any surface, you have to choose a Gaussian surface, a closed surface, dotted with the electric field on that surface. So everywhere on that surface, find the dot product between the area element and the electric field. And once you know that volume, this is a Q enclosed over epsilon naught. So let's consider the case R less than A. That's the first situation we consider. R less than A. If this is A, you want to consider a volume that is less than A. Since we have a choice, we can actually begin with any surface. So let's be judicial since we want to know inside. So you will pick a surface of this kind. So that's a sphere. Basically, it's a spherical shell, and you want to calculate the electric field everywhere on that radius. And pretend that to be of radius R. That's a radius. So that's the volume, but we assume that electric field is spherically symmetric. So this is R dotted with E. So we immediately say dA times R hat. Why is this? Because area element is always normal to the sphere. That's the direction of the area element. This is the area element itself. It's always perpendicular to the to the sphere, right? So that's this vector down here. But the electric field is also radial because it's spherically symmetric. Notice there are few arguments going on. That's the electric field, and that's the area. Area is normal because it's a sphere, and electric field is normal because we are saying that it is spherically symmetric. So there are some assumptions involved in there. And what is Q enclosed? That's equal to 0. There is no charge in there, right? So this is, charge density is 0. So that's equal to 0. Electric field can come out of this because it is spherically symmetric again. So here we assumed that dA is equal to dA times R hat, and electric field we assumed is electric field, which is radially dependent, times R hat. But this is a constant inside the surface, so it can come out. So it is E of the radius of that Gaussian surface times the surface integral. So we're still on that closed surface integral, but this is a scalar surface now. Earlier it was a vectorial surface, which could be 0. So that's equal to 0. So this is not 0. A quantity multiplied by a non-zero quantity is equal to 0. That implies that electric field is 0 everywhere inside. And we have assumed that R is less than A. Okay, notice the arguments that's going through. Now let's say R is, I think maybe one of the, let's go in systematically. So now let's say R is less than B and less than A. So again, do the same idea. It is spherically symmetric. So this is now we choose our area to be, or the Gaussian surface to be somewhere in between. R is less than that, so our surface has changed. Otherwise, nothing changes. So the arguments remain the same. It is still R hat for that Gaussian surface. Electric field, again, we assume to be spherically symmetric. It stays the same everywhere on the surface. But now the charge enclosed, what is that equal to? I have to find the charge enclosed in this region until radius R. So how do I figure that out? So I do an integral. So this is 1 over epsilon naught integral dqr of the charge density. I integrate this quantity, but that integral says that I have to go only from R. So let's say, I think I should be careful here. Let's say R prime, right? Because I'm already using the radius as a R, right? So there is a radius of the sphere that is R, so I shouldn't be using that for the volume integral. Is that clear? I chose R to be the radius of that particular sphere, and volume integral usually is a dummy variable. I have to use some other variable because after the integral it won't exist. Christian?
Yeah, inside the row equation, is that R vector?
That's R vector, and it is primed. And this is the same prime there. So I have to integrate over a variable R prime, which runs everywhere in the side of this region. Right. So if I were to show this better, so this is A. Right, so this is A. This is my radius R. And there is an R prime, which is somewhere in between. I have to scan this R prime everywhere inside this dotted line sphere and the radius A. Is that clear? Okay, so that's what this integral means. And I have to integrate less, so R prime is less than R, but greater than A. So that's its limits. In them. But as far as angular integral goes, it goes everywhere. All the angles are being covered, but the radius doesn't go beyond R. Right? Right? So if I do this again, so this is equal to 1 over epsilon naught. So let me write this more specifically. So there is a r square dr sine theta d theta d phi. This is the volume integral in spherical coordinates. R square dr sine theta d theta and d phi. Right? That's the length scales that comes in. Three integrals. Angle, it goes everywhere. Pi goes from 0 to pi. I do the whole angular integral. Phi goes from 0 to 2 pi. But r goes, oh, again, I forgot r prime. Right? R prime integral goes from a to r. And charge density, we are given that this is k over r square. Any questions on that? Charge density and this volume integral I have explicitly given. And since I'm going only from a to r, so that's the limit here. And this is a, not 0. Okay. Left hand side stays the same, I can, so this is equal to 1. And electric field comes out. And it is surface area of that sphere we are talking about. Clear? So now do this integral. What is the integral of d phi? There is no angle in this integral. So 0 to 2 pi of d phi would be 2 pi itself, because there is no variable in there. So it is d phi going from 0 to 2 pi. This will be 2 pi itself. There is no angle here. Sine theta d theta. What's the integral of sine theta d theta equal to? That's 0 to pi. That's cosine theta. Evaluated from 0 to pi. That's, oh, what is happening? That's minus right here. Sorry. So that's equal to 1 minus of minus 1. So that's minus of minus. What's happening? Yeah, minus of minus 1. So that's equal to 2. So that integral is 2. That's what gives you the surface area as 4 pi. Right? So that's where the 2 comes in. And again, I messed up again. This is r prime. Right? R prime. So this should be r prime. So that's equal to, let me write that. So this is 1 over epsilon naught, 4 pi, coming from the angular integrals. So angular, that's what is called the solid angle is 4 pi. And r prime square cancels out. K comes out of the integral. I have a to r dr prime. And that's equal to 4 pi over epsilon naught k times r minus a. That's it. The left hand side we can work on this. This is the surface area of the sphere. What is this area equal to? So one should be careful here a little bit. This area has two surfaces, right? One is down here and one is down there. Right? There are two surfaces, but even if we forget to do this, it doesn't matter because the electric field everywhere at that point is 0. Right? So it doesn't matter. But in another problem actually that could play a role. So actually that is also assuming that the volume is here. I never said that this is this actually is a closed surface. So it doesn't, I can either close it here or close it here. That was my choice. So if I say that the volume is completely from the zero, then I don't have to worry about it. But if I were to go from here, even that is possible, but because it seems like we are going in that volume, because 0 to A doesn't contribute, even then that would be okay. So there are two ways of doing it. But if we do it for the whole sphere, this is E of R times 4 pi R squared. So we get the electric field, right? We just have to divide it out. So this implies that electric field is equal to divide out by R squared. So it is K over epsilon naught. 4 pi cancels out, and it is R minus A divided by R squared. How does it go? Notice that at R equal to A, electric field comes out to be 0. And at R equal to B, it is B minus A over B squared. And everywhere beyond that point, so let's, so there is a 1 over R and there is a over R squared. So we should know how to plot that, but we'll come to that. First, let's get the outside electric field, then it will be possible to just connect the 2 points, then we will know a reference point as to where it is. That's another way of doing it. If you're not familiar, you can even plot it. Right? If you have a plotting software, you can just solve it. So there are various ways of doing it. Algebraically, any questions at this stage? So let me do the third part. So for B less than R, this is the easier one. So now we take R outside the radius B. Again, we do dA R hat dotted with R hat times the electric field. That's equal to, this time we are going all the way. So this is 1 over epsilon naught. Only difference is that now we go from A to B. In fact, we go from 0 to R. So in principle, this should be 0 to R. R prime square dr prime sine theta 0 to pi, and that is 0 to d pi d phi. And that's K over R squared. But this contributes only when it is from A to B. So we change this limit and immediately say that, oh, that contribution is 0. Otherwise, we are to write that whole expression in there to accommodate our format. Again, this is 4 pi because that's a solid integral. This is E times 4 pi R square again. That's 1 over, again, prime. I keep forgetting that. Prime square. R prime square cancels out. And you get 4 pi times K times B minus A this time. And you have electric field, it's equal to 1 over K over epsilon naught times B minus A over R squared. Notice again, so since we know that it is 1 over R squared should be your electric field due to a spherical charge, this is the same as 4 pi times k times b minus a divided by 4 pi epsilon naught times 1 over r squared. That's just another way of writing. What is the total charge on the sphere? What is the total charge on the sphere? Even though I haven't given that to you. Anyone? How would you go about doing that? Suppose you are algebraically do it, but it's an easier question than that. Look at this expression and think. So this is for R. So let me summarize. So this is the answer at this point. So let me write down. So electric field as a vector for R less than 0, that's 0. So this is for R less than A. For between the 2 points, we have this track. So let me write that as just a way of writing it. So this is 4 pi k over 4 pi epsilon naught times r minus a over r squared. This is for r less than a, or for less than b, less than a, and outside it is 4 pi k times b minus a over and my question is, just looking at this, staring at this expression, is it possible to deduce or is it possible to find out what is the charge Q on this whole sphere, on this whole geometry? Very good. So that this quantity has to be charge Q, and why is that? By definition of the electric field outside a spherically charged distribution, it should look like a point charge, right? The total charge Q shows up because outside and inside, or sitting outside, we don't know what's the structure inside. We only, so for a spherically distributed charge, what did I say? For a spherically symmetric charge distribution, the electric field sees only the charge outside. So this has to be the total charge. Another way of verifying it is that you do the volume, right? So if you do the in total dqr for once you're outside, right? So R greater than B. So this should come out to be Q. And this pretty much, we did this integral. So this is an extra credit. It's nothing, so we have almost done this integral here, or I say almost, we have exactly done this integral here. But what you have to do is that we have to equate this to Q, because charge density integrated over a volume gives you Q, and that is an answer for that. And of course, this will come out to be this. Okay, is that question clear? So it's this integral that you have to do. When you substitute this, it is this. That's your d cube r. And if you do the integral, you'll pretty much get this. And so that gives you a we should be able to plot this. So let's say if you were to plot this, so there is r, there is a b, and there is a A. And that's your electric field. Somewhere up till here, so the reference, and that's your 4 pi k b minus a over 4 pi epsilon, right? So let me write that as q over 4 pi epsilon naught 1 over r squared. So that's your q, right? This squared quantity is your q, and from that point on, it is 1 over r squared. So that's 1 over r squared. It's it's equal to 0 up till here. So it has to increase from here to there, because at r equal to a, this is equal to 0. And for c, every point beyond that point, so it has to increase, and it seems to increase like 1 over r. So there is a 1 over r in there. So there is a r minus a divided by r squared, which is equal to 1 over r minus a over r squared. So it's not 1 over r, it's 1 over r squared. So it is gradually going to increase. It's not going to increase linearly. So that's a linear form, but there is more charge at the center. So what is this? Is this it will be positive or
Concave down
it will be concave, right? So that's what I was wondering, if that or this, because I think it will slowly increase, but then when you catch up like this, I think this will be like this. But check this.
there. I thought it would be the other way.
Other way? Okay, I was afraid of that. Okay. So you're saying, and what's your argument for that?
That it would increase. Oh, well. I thought that, yeah, the largest increase would come towards A because more of the charge.
Because there's more charge in there.
I don't know.
But the radius is also small there, right? So how we go about that is usually volume. So it is r minus a over r squared. So that's your so small.
So as r gets just above a, it will be divided by a small number, a small integer.
That's correct.
Therefore, as a small integer or a small value is squared, it will be smaller than the numerator, right? I'm thinking of like less than 1. When r is less than 1.
And why is r less than 1? You're telling r greater
Assuming
than,
that's less than b, right? Because that means that it's not outside the sphere.
yeah.
I don't know. I thought Christian was on the right path, though.
Yeah, I think you're thinking correct. Okay, what you mean to say there is that you want to take out the a. So probably you want to say this one, right? So this is r over a the whole square. Right, then we are talking about r greater than 1. So if it is r greater than 1, this is larger than this smaller. Okay, so this will be smaller. So I think this is how I think it will be this way.
My only
Did you plot
argument would be, I did it wrong.
Yeah, that's
I'm
okay.
like,
That's okay.
But like, so when R crosses the threshold of A, there's a huge spike in the
I agree.
charge. So that should like kind of be, and
It's
then
not-
as it approaches B, it's gaining less and less.
But the
charge.
volume is small. Notice?
Uh-huh.
Right?
Yeah,
So
so
that is a
this
volume
becomes
gives you an
size.
r cubed.
Mhm.
So that will beat it.
Okay.
I think so. So,
Yeah.
so check it out. So my argument is this is r over a. So let's suppose this is x minus 1 over x squared. That's the plot starting from here. Right? So x equal to 1. So this is pretending now that this is 1, the way Riley was suggesting. So it's x minus 1. That's a smaller number over 1, a number that is larger than 1. So that is probably less than 1. So once it starts from here, I think it will stay there. So I think it is something like this. Is that what you were trying to suggest, Riley? Probably.
No, but I'm gonna see if I'm correct. I accept your answer. I'm just gonna see if I am wrong.
I'm just looking at here and doing this. So this is check, right? And another extra credit. check is I think that's okay. A blunt check would be instead of looking at the pattern, so this is x minus 1x.
Right. So I did a blunt check just
just-
now. I did 1.1, like x was equal to 1.1,
Yeah,
and I got a decimal above 0.9, and then I just did 1.5, and I got a decimal of 2/3.
exactly. So,
So it
no,
started
not
off as a spike, and then it is. Oh, I didn't do -1 though, so it would be.
no, so this is 1, so somewhere here, right? Put 3 by 2. So x is equal to 3 by 2. Correct?
Yeah.
So because we want larger than 1, correct? So this will be equal to 3 by 2 minus 1. That's 1 by 2 divided by x is 9 by 4, right? So that's a large number, I suppose. Right? So that's 2 over. So this is not even like this. I think it goes up like that. So check on that. Yeah.
Quick question.
Yes.
I already submitted my homework. Can I turn in a different homework?
Yes. I think that what happens is that until I grade it, you can keep replacing your homework. I'll see only the last submission. I don't think I even have access to your earlier submissions. So it's only the final document that you see that's I see. I think probably you also see all
And then you have.
I think in one of my other classes, like last semester or 2 semesters ago, I tried to do it and it was kind of locked out. Like once I submitted one, I couldn't submit anything else.
That's probably correct because that's an option in D12 that you allow one submission, multiple submission, and if it is multiple submission, do I want to see all the submissions or only the last submission? I have set it that I want to see only the last submission. So that's all I said.
Thanks.
Yes. Yeah. Okay. Is that reasonable, clear? Any questions on that?
Yeah, I think that actually you're correct. Just hammering it away on the calculator. I came up with the same solution you did. So yeah.
Okay. Good. Yeah. I'm thinking of is there another better way of interpreting this plot? Usually there are, but I'm not. Yeah. Yeah. Okay. So. Seven minutes. So I was a little concerned that this was. How about introductory level physics? Have you guys seen this kind of problems? No.
I wasn't a big fan of my 205B professor. I don't think I got much out of it at all. So.
Yeah, Bryce already. Yeah.
For these examples,
This is not familiar to me from that class.
Okay. Matt, Curtis, and Riley. Have you seen this before?
This equation, like this work?
This kind of works. So given the charge density to find the electric field, to get this plot from whatever
I think we briefly touched it in 205B, but I don't remember it that much.
Oh, you might have taken it with me actually. Yeah. What about Curtis?
I don't remember doing I don't think so. I think we did similar problems, but I don't think we actually plotted.
No, we never discussed the theory behind it or anything like that, like what is actually happening. And I took 205B with Russell.
Gotcha. And Matt?
Yeah, I think kind of what Riley said. Like, it kind of looks vaguely familiar, but I don't know
If it is vaguely familiar, I can see because you go through this in one lecture because 205B goes very fast, right? And the Gauss's law. Even when I do it, it's just one lecture. But then I don't go this slow. I really go fast, and which is ironical. That you're seeing it for the first time. Okay, so what I will do is then I won't construct harder problems than this. This is the hardest problem. What will change is that it will become cylinder. Can you see the difference between what's going to happen if it is a cylinder and a sphere? Yes, so in this integral, so for example, if this was a cylinder, so let's say cylinder. Right? So cylinder, so the diagram looks exactly the same. So now the only this geometry is coming out all over. And let's do what is the electric field inside. So again, you would pick something like this. So this will be an exam problem, but I'm giving you sufficient hints. And look up your textbook also. This is a good point to read the textbook. Textbook really goes over Gauss's law pretty extensively. So that's one place to examples. I think this is examples in the textbook. Or for that matter, just look up Gauss's law for cylindrical geometries or spherical geometries on the internet. It's, that should be sufficient stuff in there if you don't like it. But book is good. So that's your R. This is your A. And let me give you some charge density now. This is R, so this is equal to, since this is a cylinder, it is better to call it rho instead of R, but the meaning is the same, it's a radius constant. So this is 0 if R is less than A, and let's say this is K over, this time let's make it R. Sorry, rho. Or A less than rho less than B, and it is 0 for B less than rho. It is usually the right hand side that that we are talking about, but let's talk about the left hand side. So that is, and this is an infinite cylinder. So cylinder of infinite length. Is that visible for those ones? Oh yeah.
Yes, it is.
So when I talk about this Gaussian surface, that is also of infinite length. So you're talking about an area element on that. That's dA, and dA this time, this is electric field. This is equal to 1 over epsilon naught. You have to integrate dz minus infinity to plus infinity if you want. And then you have what is the volume integral of a cylinder d cube r prime for a cylinder? The d cube r for a cylinder is rho d rho dz and d phi. Right, three integrals, but instead of r prime, there is only rho d rho now. So that's rho d rho, and let's do this in prime variables. That's prime, prime, prime. Now I go from A to B, and that is an angle d phi going from 0 to 2 pi. And this is k over rho prime. Notice that I purposely made this rho so that that cancellation still happens. But in principle, you can do this for anything. It could be rho prime square or what sort. It will just become a different integral. That's all. Now, notice that I have a choice on this Gaussian surface. Usually what you do is that this Gaussian surface is made of length L. That's coming out of the board, you make it of length L. I can choose anything I want. That way I don't have this infinity. Right? 0 to L. On the left-hand side also it's the same. Correct? So this cylinder now is coming out of the board from 0 to L. Is that clear? This surface, since it is 0 to L, so there is 3 pieces to that. Cylinder plus disk plus disk. Is that clear? Again, if it is not clear, look it up. There are nice diagrams where they explain this clearly. There is a cylinder, disk plus disk. On the disk, the contribution is 0 because electric field is parallel to that face and the area is perpendicular to that. On the disk contribution, so on disk, area vector is perpendicular to electric field, which means it is 0, implies no contribution, 0 contribution. Can you guys imagine that? No. So let's look at the face. So this is the dotted surface here. So that's a surface. Electric field is perpendicular to this. This is radial. Electric field is all radial, but the area vector only on the disk is coming out of the board. So dA is in the direction of Z, and electric field is in the direction of rho hat. These two are perpendicular, so that doesn't contribute. So on the disk, there are 2 disks that is capping the cylinder, and that is the surface of the cylinder. On both the caps, the contribution is 0. Is that clear?
Yes.
But how come if a point charge and it's in all 3 dimensions, why wouldn't the
Charge is there all through, infinite.
Right.
Right? So let me draw this out this way. This goes all through. Right? I draw this back. Okay. Charge goes all through. So as you're saying, so let's think of a positive charge here, right? There is an electric field here, and you would say that, oh, this also has an electric field here and a here. Right? But there is also a contribution from this side, from this point. Again, there is electric field here. At this point here, these two try to cancel out, and that keeps going on. You have to keep adding from all the infinite pieces, and always these components will cancel out just by symmetry. And one has to actually do that, but Gauss's law, what it does is that does it for you. This is not very obvious that this will happen, but Gauss's law actually proves that this happens. What we will do in the next 2 weeks or so is that do these integrals explicitly. Whatever Gauss's law does that for very symmetric surfaces. For example, if I were to cut the cylinder and then ask what is the electric field, Gauss's law fails because symmetry is no more there. There we will actually explicitly evaluate that. So that's what is going to be the exercise later. Now we are doing it for symmetric systems. So just because it is infinite, our Gaussian surface is finite. I think maybe that was a confusion. So this is finite. This is of length L. But the cylinder is infinite.
Okay. Yeah.
Right? This is finite. So it's only our observation cylinder that is finite, but the cylinder actually is infinite, so it cannot have any components in that direction. Does that help?
Yes. Yeah, because I was worried about charge on the end of the cylinder. It doesn't have anything to cancel.
There is no end of
There is no.
This is a Gaussian surface, our observation surface. Right? This is not a physical surface. I'm just doing a mathematics on that surface. right? But the physical cylinder is infinite, so this keeps going. So keep that in mind. Look it up also. Books really explain this part very well. Look 205 books, those are all, and they go over this very carefully and in a lot more detail. The point then is that overall, after doing all this, what we get is, so let me, you guys are available for 5 more minutes? You have a class?
No, I'm good.
Okay. So the surface area of the cylinder then, this doesn't contribute, is 2 pi times the height of the cylinder, which is length L, times the perimeter of that, what is that? No, 2 pi times rho. So that's the perimeter of that cylinder times length L, right? If you had to open up the cylinder, it has a length L and the side is 2 pi rho. So that's your area there times electric field, which is what we are looking for. That's the left hand side. On the right hand side, I again have the length L. That's important because I want to cancel that. Like this was an observation cylinder, remember, that was our choice. It shouldn't depend on that preferably. Right? So that cancels out nicely. And this rho prime cancels out. D phi is 2 pi. So I get 2 pi times K times that B minus A. Like if it was, if I'm going only till rho, so this will be rho minus A. There I'm doing the total charge. So L cancels out nicely, 2 pi also cancels out, but let me write that in a certain form. This is equal to 2 pi K rho minus A divided by 2 pi epsilon naught. And since I usually want to write it like 4 pi, let me write it as 4 pi and multiply this by 2, right? So this is 4. So this is 2 pi and then a 2. And that is 1 over rho. Notice that electric field due to a point charge was 1 over r squared. For a cylinder is 1 over rho. So a point charge and a cylinder is like a line, right? So this is a point charge. If I make a line out of points, that becomes a line which is a cylinder. This is 1 over r squared. It's 1 over rho. How can I extend this further? If I go to the next dimension, point, line, and a plane, right? So the next is a plane. So 1 over r squared, 1 over rho, what should be the next, right? So this is plane. What is the electric field due to a plane, infinite plane? Any idea? You can look at this pattern or you can think of from 205. What's the electric field close to a plane? How does it go? Is it 1 over r squared? Does it grow?
Doesn't depend on the radius.
Does not depend on the radius, constant, right? This is rho raised to 0. The r squared or 1 next one is 0, right? So this will be constant. Right? That's like saying it's a sphere, like right next to the surface of Earth, we have constant gravity, right? That's like saying it's a flat plane. We're so close that we don't see the radius of the sphere. It looks pretty much flat, right? So that's how it is. So yeah, I'll try to, yeah, whatever question I make, it will be 205 based. So look for 205 books or your textbook pretty much. It just goes into detail. Okay, so yeah, I hope I don't make it very hard. Little worried since you guys said the homework was a long time.
Yeah, I don't think the homework was hard or anything. I think that I just took the wrong approach at it.
Okay.
Yeah.
Look up again. The advice is look up. Look up literature. I mean notes of that. Gauss's law for a sphere, Gauss's law for a cylinder, something like that. You should.